In this problem, we're going to work with directional derivatives and the gradient. The problem says consider the function f of xy equals 2x squared plus y squared. Part A is compute the directional derivative of f in the direction of the vector u equals root 3 over 2 1/2 at the point 2, -1. And then part B is to find the vector, the unit vector in the direction of the steepest ascent and the rate of ascent at 2, -1. Okay. Well, part A is pretty easy. So the directional derivative is just the dot product with the gradient and the direction that you're going. So first we find the gradient. That's f sub x comma f sub y. That's going to be 4x comma 2y, right? Because you just take the partial derivatives and you evaluate. So this is happening at the point 2 comma -1, right? So that's the point AB that we're working with. And so you want to find what the gradient is at the point AB, and that's going to be what you get when you evaluate the gradient at 2, -1. That's going to give us 8, -2. So that's the direction of the steepest ascent, or at least the non-normalized vector, right? It's the gradient. Now the directional derivative is going to be the gradient of f and AB dotted with the unit vector in the direction that we're interested in. And so you take this vector 8, -2 and you dot it with the vector root 3 over 2 1/2, and then you're going to get 4 root 3 minus 1. So that's the directional derivative. That's a slightly positive number. Actually, that's not just slightly positive, that's a positive number. And so f is increasing. If you start at the point 2, -1 and head in the direction of u, the function is going to be increasing at the rate of 4 root 3 minus 1. And then part B says find a unit vector in the direction of the steepest ascent. Well, that's just the gradient, right? That's just the gradient except normalized so that you have the unit vector. So it's going to be this vector divided by the length of the vector, and the length of this vector, so we have 8, -2 divided by the square root of 8 squared plus -2 squared. And that's going to be the square root of 64 plus 4 is 68. So you get 1 over the square root of 68, 8, -2. Or if you want to simplify this, since the square root of 68 is 4 times 7, 4 times 17. So then when you take out the 4 from the square root, you get 1 over 2 root 17, 8, -2, and then you can divide by 2, and you can get 4 over root 17, -1 over root 17. That's a more simplified way of writing it. Okay, but we're still not done because we still have to find the rate of the ascent, right? So if you're at the point AB and you head in the direction of the gradient, then that's going to maximize the rate of change of the function. And actual rate of change is going to be the magnitude of the gradient. And that's going to be, so the rate of change, or the rate of the steepest ascent, is the magnitude of the gradient, which we found is the square root of 68. And remember, the rate of ascent or descent, the rate of change of the function in the direction u is just the gradient of f dot u. So let's just recall why the rate of steepest descent is the magnitude of the gradient. It's because when you take the gradient, evaluate at AB, and then take the dot product with the direction of steepest descent, so that's just the gradient divided by the magnitude of the gradient. Okay, this thing is a constant, and you have this dot product of this vector by itself, and then that's going to be equal to the magnitude of this vector squared. And then you have this same thing at the bottom, and when you divide, you can cancel out the magnitude of the gradient from top and bottom, and you're just going to be left with the magnitude of the gradient. So that explains why the direction of steepest descent is the magnitude of the gradient. This is just an aside, this is just a review. Okay. To explain why the rate of steepest descent is the magnitude of the gradient. In general, it's just the directional derivative. It's the dot product of the gradient with the unit vector that you're going in. Okay, so a pretty simple problem. I mean, there's not really much to it. It's just a matter of, do you remember the facts that you need to solve this problem?